Imagine you're tasked with mining an asteroid. Like, your first instinct is probably ripped straight out of a sci-fi movie,
Oh,
right?
absolutely. The classic Hollywood approach.
Yeah, exactly. You
Yeah.
build this massive, glittering spaceship. You fly out into the deep dark, snag a million-ton rock with these giant mechanical claws, fire up the engines, and drag that massive mountain of treasure all the way back to Earth orbit.
Right. It sounds totally heroic.
It does. But what if physics dictates this is the absolute worst way to do it? Because it turns out if you try to physically drag an asteroid home, your mining robot will spend like 13 straight years doing nothing but grinding rock just to fuel its own engine.
Yeah, it is a mathematically doomed approach. I mean, the brutal reality of space is that dragging a mountain across the solar system requires so much energy that the mass of the fuel begins to outweigh the value of the cargo.
Wow, so you're losing money before you even start.
Exactly. The physics of orbital mechanics and material throughput, they just ensure that this right-at-home megaship is an approach that basically guarantees failure before it even leaves the launch pad.
So today, for our deep dive, we are looking at the actual architectural blueprint for autonomous space mining, paired with some really foundational research on self-repairing legged robots.
You're right. We're talking about how to physically execute this, not with brute force, but with a swarm.
Yeah, a swarm of these robotic scout tugs that island hop across the solar system, manufacture their own gravity, and refine metal without ever actually melting the rock.
Which is mind-blowing when you think about
It
it.
really is. And to you listening, we aren't dealing in abstract theories today. This architecture is built on strictly grounded numbers, existing metallurgy, and the absolute limits of microgravity.
Yeah, no magic technology here, just physics.
Right. So let's start with the math that breaks that sci-fi dream. The architectural papers we're looking at completely discard the idea of the megaship based on one single variable, which is throughput.
Throughput is essentially the silent killer of space infrastructure. I mean, the entire design conversation shifts the moment you realize the limiting factor in space mining isn't the rocket equation.
Okay.
And it isn't the availability of fuel either. It is the raw physical rate at which a single machine can chew through solid rock and feed it through an engine.
But, okay, wait. If we're utilizing nuclear propulsion, which this architecture absolutely requires,
Yeah.
my intuition is to challenge that bottleneck.
Sure.
Because if we have a nuclear engine, we possess an almost unimaginable energy density.
Hmm.
Why is throughput such a massive wall if we can just, strap a reactor to the rock and push? It seems like it should just be a matter of generating enough thrust.
Well, to understand why raw thrust doesn't solve the problem, we need to look at the mechanics of a nuclear thermal rocket, or an NTR.
Okay, lay it on me.
So unlike the chemical rockets we see launching from Earth, which burn a refined fuel and an oxidizer to create this high-pressure explosion.
Like SpaceX or NASA launches, right?
Right. An NTR doesn't combust anything at all.
It's essentially just a giant heat exchanger in space, right?
Mechanically speaking, yes. You have a fission reactor core, typically utilizing enriched uranium, and it operates at extreme temperatures. So to generate thrust, you basically pump a propellant through the channels of that blazing hot core.
And it just heats up and shoots out.
Exactly. The propellant absorbs the thermal energy, expands violently, and shoots out of a supersonic nozzle at the rear. The physical reaction pushes the vehicle forward, so the energy comes entirely from the nuclear fission.
Which separates the exhaust energy completely from any chemical combustion limits. And we know this works, right? Because the U.S. actually ground-tested Nervia and Rover engines back in the 1960s at Jackass Flats in Nevada.
Yeah, they proved you could have sustained restartable nuclear thermal operation. They ran hydrogen through a graphite core.
Okay, so if the engine technology is proven, where does the physics bottleneck actually come in?
It comes from the governing equation of thermal rocketry. The exhaust velocity, which dictates your efficiency scales roughly as the square root of the temperature divided by the molecular mass of the propellant.
Okay, so the equation is the square root of T over M.
Precisely.
So T over M. The temperature's in the numerator, so obviously you want the reactor as hot as possible to maximize your exhaust velocity.
Right, but that has a hard physical ceiling.
Because if you run the reactor too hot, the uranium fuel elements and the containment vessel will simply melt, right?
Exactly. The material science of the reactor core imposes a strict limit on T. That means the only variable you actually have control over when designing your mission is the denominator.
The molecular mass of the propellant.
Yes, you need the lightest possible molecule to achieve high efficiency.
Which is why those NRV tests use hydrogen. I mean,
Yeah.
with a molecular mass of just 2, Hydrogen gives you a specific impulse, or ISP, of around 900 seconds.
Right, which is roughly double the efficiency of the best chemical rockets flying today.
But out in the asteroid belt, you don't exactly have massive cryogenic tanks of pure hydrogen lying around waiting to be used.
No, you definitely don't. And hydrogen is incredibly difficult to store long-term anyway. It boils off, it leaks right through metal matrices, and it requires heavy refrigeration.
So you basically have to use what you find.
That is the beauty of the NTR. It is chemically indifferent, it doesn't require a combustible mixture, it only cares about having a mass to heat up and expel.
Like whatever is lying around.
Yeah, you can pump water through it, or you can literally even pump vaporized rock.
Okay, but if we look at the denominator in that equation again, water has a molecular mass of 18, which drops your efficiency down to an ISP of about 350 seconds.
Right.
And vaporized rock, I mean, that's composed of complex silicates and heavy metals, so its mass is around 60 or more. Your efficiency plummets to maybe 200 seconds.
Yeah, it's terrible.
That is worse than a rudimentary solid rocket booster. Why would an architecture actively choose to run a nuclear reactor on vaporized rock with such terrible efficiency?
Because it completely subverts the standard economic model of spaceflight. I mean, efficiency in terrestrial rocketry is heavily focused on getting the most push out of every kilogram of fuel.
Because lifting that fuel out of Earth's massive gravity will cost thousands of dollars per kilogram.
Exactly. But out on an asteroid, the rock is already there. It is fundamentally free. It never had to be lifted off a planet.
Oh, I see.
So a highly inefficient engine running on free, locally sourced rock vastly outperforms a highly efficient engine that requires you to manufacture, launch, and transport liquid hydrogen from Earth.
Okay, it makes total sense economically, but this is exactly where we slam into that throughput wall.
Yeah, this is where the math gets brutal.
Let's look at the baseline target in the architecture. It's a generic 100-meter rubble pile asteroid. The documents calculate that a body of this size weighs roughly 1.05 million tons.
Right.
To push a 1-million-ton rock back to the Earth-Moon system using a low-efficiency rock vapor rocket, we have to grind up part of the asteroid to use as the propellant.
And the mission calculations suggest you would need to consume roughly 40% of the asteroid's total mass just to generate enough propellant to move the remaining 60%.
Wait, 40%? That is over 400,000 tons of solid rock.
Yes, and you can't just drop boulders into a nuclear reactor. The heat exchange requires fine particulate matter to flow smoothly through the core channels.
So you have to physically grind 400,000 tons of asteroid down to a fine dust.
Exactly. And the architecture cites the bond work index, which is it's a standard metric in terrestrial mining for the energy required to reduce a rock size.
Okay, and what does that look like for an asteroid?
For typical asteroidal silicate, it takes about 15 kilowatt hours of comminution energy just to grind a single ton.
And that energy requirement dictates the physical size and capability of the machine. The propulsion itself isn't the bottleneck at all.
Not at all. A gigawatt-class Nervea reactor could easily blast out hundreds of kilograms of vaporized rock every second. It could finish the entire orbital redirect burn in a matter of weeks. But the bottleneck is the grinder. It physically cannot keep up with the reactor.
Okay, let's run the math on that. If we assume a massive heavy-duty mining robot that can grind 1 kilogram of hard rock per second, which, by the way, is an incredibly aggressive, high-wear industrial rate for an autonomous system operating in a vacuum.
Yeah, 1 kilogram a second is pushing it.
Grinding 400,000 tons at 1 kilogram per second takes roughly 13 straight years.
13 years of nonstop high-friction grinding 24/7 just to feed the engine enough propellant to execute the transit.
That's insane.
And that is before the machine has even begun processing the asteroid for the valuable metals it was sent to retrieve in the first place. It is an engineering absurdity.
It's like trying to shovel a massive snowed-in driveway with a teaspoon. You possess a massive power source, but you simply cannot force the physical material through your processing system fast enough.
That's a perfect analogy. If a single megaminer requires over a decade just to fuel itself for a single transit, the escort architecture is defunct.
Dead in the water.
Exactly. The robot's most precious resource is not its fuel nor its thrust. It is its operating time. Autonomous machines operating in a high-radiation, high-abrasion environment without the possibility of human maintenance have a finite, irreplaceable lifespan.
So spending a decade coasting through the void, doing nothing but slowly feeding a grinder into an engine, That's just a catastrophic waste of that machine's operational life.
It is, which means if we can't ride it home because grinding the propellant takes 13 years, the only logical alternative is to impart the thrust and then decouple.
Which shifts us into the second major phase of this architecture, the swarm and the island hopping route. Instead of one massive ship escorting one rock, we deploy a fleet of comparatively light, modular scout tugs.
Right, because the physics of orbital mechanics are entirely indifferent to whether the robot stays attached to the rock.
Right, the rock doesn't care.
Exactly. The change in velocity required to alter the asteroid's orbit so that it intersects with the Earth-Moon system is identical in either scenario. What the impulse and leave fleet achieves is the recovery of the robot's operating time.
So the tug arrives at the asteroid, anchors itself, grinds just enough local fuel to impart a specific redirect impulse, fires the nuclear engine, and then it just lets go.
Yep, it drops the mic and leaves. Gravity and orbital momentum do the rest of the multi-year transfer for free, while the tug hops to the next target.
So a single machine could redirect dozens of bodies in the time an escort miner would take to move one.
It transforms a bespoke one-to-one escort mission into a highly scalable, parallelized supply chain. But detaching the robot from the million-ton payload introduces a severe hazard.
Yeah, that was my immediate thought. We're essentially playing cosmic billiards with million-ton rocks, right?
Basically, yeah.
Yeah. Applying a massive push, turning our backs, and hoping they magically arrive in Earth orbit years later. If the initial burn is slightly misaligned, or if the rock experiences asymmetrical off-gassing during its coast, aren't we risking a catastrophic Earth impact? Like a dinosaur extinction event?
A coasting million-ton body on an Earth-approaching trajectory with no active control system is a definitive hazard. Small perturbations, such as the Yarkovsky effect.
Wait, what's that?
It's where the tiny continuous push created by sunlight re-radiating off the warm side of a spinning rock can shift an orbit. Over a multi-year coast, that tiny push can alter the trajectory by hundreds of thousands of kilometers.
Wow, just from sunlight.
Just from sunlight. Therefore, the architecture dictates strict, non-negotiable fail-safe rules.
Okay, let's go through those. The first rule is trajectory isolation. Aim to miss.
Mm-hmm.
You never target a direct Earth intercept.
Right.
The fleet calculates burns targeting a lunar distant retrograde orbit, or DRO. It's a highly stable, high-altitude orbit around the moon where the gravitational pulls of the Earth and moon balance in a way that traps the object.
So if your initial push is slightly off, the fail-safe result is that the asteroid harmlessly misses the Earth-Moon system entirely and continues orbiting the sun.
Okay, so no dinosaurs dying today. And the second rule is that the payload is never truly abandoned. While the primary mother tug moves on to the next target, it leaves behind a highly simplified Shepherd child robot attached to the rock.
Yes, and this Shepherd requires very little power. It utilizes small trim thrusters to make microscopic mid-course corrections during the years-long coast.
Just counteracting those thermal drifts and ensuring the rock hits the exact capture corridor for the lunar DRO.
Exactly, and then the third rule caps the size of the target, which relies on a fascinating piece of physics. We strictly target small rocks, roughly 30 to 100 meters across.
Because a 30-meter rock is thousands of times lighter than a 100-meter rock. If a 30-meter rock somehow breached all the fail-safes and hit Earth, it would largely ablate harmlessly in the upper atmosphere.
That's the safety aspect, yes. But there is a deeply mathematical reason related to angular momentum that dictates why we must target small rocks. It is known as the R to the fourth wall.
R to the fourth wall. Okay, explain that.
Well, before you can apply a steady directional thrust to an asteroid to change its orbit, you have to stop it from spinning. If the body is tumbling end over end, your rocket engine will just push it in chaotic circles.
Right, you just do a cosmic cartwheel.
Exactly. You have to despin it. And the cleanest way to despin an asteroid without wasting imported propellant is to use the asteroid's own mass.
So you grind up some rock, position a mass driver on the equator, and fling the material out into space in the opposite direction of the spin.
You got it. But the amount of angular momentum you have to cancel scales geometrically. The moment of inertia of a spherical body scales with the fifth power of its radius.
The fifth power.
Yeah. So when you calculate the mass, you must throw from the surface at a given velocity to halt that spin. The required mass scales as the radius to the fourth power. This R4 scaling creates an absolute physical barrier.
Wow, okay, the numbers clarify just how fast this scales out of control. So for a 100-meter body, flinging ground rock into space at 100 meters per second. It takes about 17 hours of continuous operation to despin the asteroid.
Right, which is a completely manageable time frame for an autonomous mission.
But if you try to despin a 500-meter rock,
A 500-meter rock is only 5 times wider, but because of the R-force scaling, the mass you must process increases by a factor of over 600.
oh my God.
It would take over 440 days of continuous grinding and flinging just to bring the rock to a standstill.
More than a year of continuous wear on the machine before you can even begin the propulsion phase.
Exactly. So large bodies are excluded not just by safety, but by the physical limits of angular momentum and throughput.
Which means we need a steady stream of tiny 30 to 100-meter rocks, which creates a massive logistical hurdle. Tens of thousands of near-Earth asteroids have been cataloged, but small, easy-to-move targets, what orbital mechanics call ultra-low delta-V targets, are faint, fast-moving, and incredibly rare. Earth-based telescopes cannot reliably track them.
Right, so the fleet cannot wait for Earth to feed it targets. It must possess a prospecting layer.
Like scouts.
Yeah, the tugs are equipped with optical and multispectral sensors. As they coast between known targets, they actively map the void, cataloging the size, spin rate, and spectral class of everybody they pass, continuously updating a shared distributed ledger of potential targets.
But they are not just looking for ore, are they?
No, they are mapping a logistical supply chain based on the solar system's compositional gradient.
The distribution of asteroids isn't random. Due to the thermal gradient of the early solar system, the so-called snow line, different materials condensed at different distances from the sun.
Exactly. In the inner belt, closer to Mars, you predominantly find S-type asteroids, which are stony, silicate-heavy, and rich in metals.
But as you move further out, you find C-type asteroids, carbonaceous bodies.
And crucially, those carbonaceous C-types are rich in volatile compounds, specifically water ice trapped within the clay minerals.
Oh, wow. This connects perfectly back to our nuclear engine. We discussed how the NTR can run on vaporized rock at a terrible specific impulse of 200 seconds. Right. But if it runs on water with a molecular mass of 18, the efficiency jumps up to roughly 350 seconds.
Which is a huge boost. Therefore, a C-type asteroid is far more than a mining target. It is a refueling depot.
A gas station in space.
Yes. The fleet explicitly maps out a route of C-type bodies. The tugs literally island hop from one water-bearing rock to the next, cracking the clay to harvest water, refueling their propellant tanks, and then using that higher efficiency water propellant to jump to the highly valuable S-type or M-type metallic rocks.
The entire routing algorithm of the swarm is dictated by the distribution of water.
It's beautiful. It is a brilliantly self-sustaining logistics network.
You launch the fleet in modular pieces on heavy-lift rockets, assemble the tugs in low Earth orbit utilizing standard docking hardpoints, fuel them up initially from an orbital depot, and send them out to the Lagrange points. From there, they multiply their capability by living off the land. But, and here's the kicker, this operational elegance crashes into physical reality the moment a tug actually reaches its target.
Oh, yeah. Landing is a nightmare.
We have our robot. It finds a 100-meter rock, despins it, and prepares to land. But what actually happens when a machine tries to dig into a rock that possesses essentially zero gravity?
It is an environment that violently rejects traditional robotics. If you place a massive 10-ton robotic mining rig on the surface of a 100-meter asteroid, it essentially weighs nothing.
Nothing at all.
The surface gravity is measured in micro to millig. The gravitational force holding the robot to the surface is mere newtons. It's comparable to the weight of a feather resting on a table on Earth.
And the ordinary purpose of a robot's legs, or the treads on an excavator, is to press against the ground to gain traction against the machine's own weight.
Right.
If there is no weight, there is no traction. It's like trying to drill into a concrete wall while standing on an ice rink wearing roller skates.
That is perfectly stated. If that robot attempts to drive a drill bit into the rock's surface, Newton's third law of motion becomes the dominant force. Every action has an equal and opposite reaction.
So the force required to fracture the rock will instantly push back against the drill, and without the mass of the robot pinning it down, the machine won't make a hole.
No, it will simply launch itself backward off the asteroid.
Which is terrifying, and it's a profound hazard that has actually occurred in practice. During the Rosetta mission in 2014, the Philae lander touched down on Comet 67P.
Oh, man. Yeah.
The plan relied on ice harpoons to instantly fire and anchor the lander, but the harpoons failed to deploy correctly, the surface was harder than expected, And the reaction force of the touchdown bounced the lander right off the comet.
It tumbled through microgravity for over 2 hours before coming to rest in a shadowed crevasse where its solar panels could not function.
Anchoring to a microgravity body is arguably the single highest failure risk maneuver in the entire architectural plan.
Absolutely. If you cannot rely on gravity to hold you down, the machine has to physically manufacture its own weight. It cannot walk. The robot's legs aren't for walking at all. They function as a rigid bracing frame.
Okay, how do they do that?
The architecture achieves this manufactured weight through two distinct operational modes. Mode A is utilized when the nuclear engine is offline and the robot is purely focused on harvesting material.
Got it.
The legs were equipped with highly specialized end effectors derived from NASA JPL's microspine gripper research.
Microspine.
Yeah, these grippers utilize thousands of tiny independent hooks that drag across the rock face, finding microscopic asperities and rough patches to latch onto.
So once the microspines secure a temporary hold, a rotary percussive drill positioned straight down the center of each foot engages.
Exactly.
It bores a precise hole into the asteroid and undercuts a groove to create a permanent mechanical anchor point. It's exactly like a mountain climber placing a pedant into a rock wall.
That's it, exactly. And once each leg has established its anchor, the robot engages internal winches to pull the anchor cables tight. That mechanical tension pulls the chassis of the robot down firmly against the surface. The tension literally becomes the gravity.
The tension becomes the gravity. That's brilliant.
Right. The rigid legs brace against that downward pull, stabilizing the platform so that the primary belly drill can bear down and fracture the rock without launching the robot into space.
So that tension solves the harvesting phase. But then there is mode B, which is engaged when the nuclear engine fires to actually redirect the asteroid.
Yes.
During a burn, the engine exhausts out the rear of the vehicle, away from the rock face. The thrust of the engine pushes the entire robot forward, driving it into the asteroid.
Exactly.
During this phase, the acceleration of the burn itself acts as the artificial gravity, vectoring straight down into the surface.
So the legs go into heavy compression, bearing the load of the thrust, and the anchor cables can actually be allowed to go slack. The machine gracefully transitions from pulling itself down to pushing itself down, ensuring it is never unweighted and never risks floating away.
Wow. Now that the robot is securely anchored, it can begin to chew into the rock. But microgravity introduces another severe complication, which is dust. You cannot use a traditional open backhoe or a drill that flings cuttings away.
No, you really can't. On Earth, gravity quickly pulls airborne dirt back to the ground, and atmospheric moisture helps clump it together.
Right.
In the vacuum of space, neither of those forces exist. Furthermore, the constant bombardment of the solar wind leaves the dust highly statically charged.
So it sticks to everything.
Everything. If a drill throws cuttings into the vacuum, it creates a hovering, highly abrasive, statically charged sandstorm.
And the Apollo missions demonstrated how lethal lunar dust was. I mean, it degraded the pressure seals on the spacesuits and scratched the optical lenses in a matter of days. Asteroidal dust is arguably worse because it never settles.
Yeah, if our robot generates an open dust cloud, it will sandblast its own joints, foul its thermal radiators, and totally blind its optical sensors.
Therefore, the belly of the robot does not dig in an open environment. It actively contains. The harvesting mechanism is fully enclosed within a shroud that seals against the rock face.
Exactly. As the cutter head fractures the material, it is immediately vacuumed or mechanically swept into an internal hopper. The entire process isolates the abrasive particulate from the external mechanisms of the robot.
Okay, so this enclosed rock is then either fed straight into the reactor to be vaporized as propellant, or it is diverted into the refinery to extract the valuable metals. But before we get to the refinery, we need to look closer at that reactor.
Ah, yes, the bimodal nuclear core.
The architecture specifies the bimodal nuclear core. It is highly centralized, performing 4 distinct roles from a single fission source.
Yeah, the bimodal nuclear thermal rocket is basically the metabolic heart of the entire machine. Its first role, as we've discussed, is a megawatt-scale thermal rocket during the propulsion phase. But its second role is equally critical. During the long, multi-year coasting phases between targets, the engine is idled, but the reactor remains active as a power plant.
How does that work?
It utilizes a closed-loop thermodynamic cycle, specifically a Brayton cycle using a helium-xenon gas mix, or a Rankine cycle using liquid metal vapor to spin a turbine and generate hundreds of kilowatts of continuous electricity.
It is essentially a miniaturized terrestrial nuclear power plant strapped to the back of the robot.
Yep. And its third role is thermal management. The deep cold of space presents a freezing hazard to the robot's electronics and chemical processing fluids.
So a keep warm coolant loop taps into the low-grade thermal heat radiating from the idle reactor, circulating it through the chassis to maintain operating temperatures.
But harnessing that reactor heat introduces the fourth role, which is radiation shielding. The fission core is emitting a lethal flux of neutrons and gamma rays that will rapidly degrade the solid-state electronics and the AI processors of the robot.
It'll just fry the brain.
Exactly. To protect the brain, the reactor is placed at the end of a long deployable boom, physically separating it from the main chassis. A dense shadow shield sits between the core and the chassis, casting a cone of radiation protection over the robot.
And the coolant loops carry the necessary thermal heat across this boom, because heat can travel via fluid convection, but the straight-line radiation cannot easily navigate the complex plumbing.
It's a very clever workaround.
That is an incredibly elegant geometry. You harness the warmth while hiding from the lethal dose. But managing heat in space reveals another completely counterintuitive physics problem.
Heat rejection.
Yes. On Earth, if an engine runs hot, we use air or water to cool it down. In space, my initial thought is that cooling should be trivial because space is near absolute zero.
Right. That's what everyone thinks.
But the architecture outlines heat rejection as one of the most massive structural challenges of the entire vehicle. Why is that?
Space is undeniably cold, but it is not a coolant. A coolant requires a medium to absorb and carry away the heat through conduction or convection. Space is a vacuum. It is a superb insulator.
Oh, wow. I never thought about it like that.
The only physical mechanism available to shed waste heat in a vacuum is thermal radiation emitting the heat away as infrared light.
And the physics of thermal radiation are brutal. It is governed by the Stefan-Boltzmann law, which states that the power radiated from a surface scales to the fourth power of its absolute temperature.
That T to the fourth scaling dictates the entire physical geometry of the spacecraft. If you have a highly concentrated heat source, like the nozzle of the rocket glowing white hot at thousands of degrees, it radiates heat incredibly efficiently.
Right.
But the waste heat from the electrical power plant or the cooling loops for the computers is relatively low-grade heat, maybe a few hundred degrees at most. Because the temperature is low, the T to the fourth efficiency plummets.
So to reject that low-grade heat, the only variable you can increase is the surface area. The cold sink is not free.
Not at all.
Rejecting even a few hundred kilowatts of waste heat requires massive, sprawling radiator panels. They will likely be the largest physical structures on the entire vehicle, towering over the main chassis just to radiate infrared light into the void.
It's wild. The vehicle must continuously balance a system that swings from a quiet, power-generating idle to a violent multi-megawatt propulsion burn, all while dynamically trimming its attitude to keep those massive, fragile radiators pointed away from the sun.
And adjusting its thrust vector to track the asteroid's constantly shifting center of mass as the robot consumes the ground beneath it.
It is a phenomenal juggling act of mechanical engineering and orbital physics.
Okay, let's synthesize where we are. We have a robot that has utilized the swarm to find a target. It has despun the asteroid, anchored itself utilizing tension to manufacture artificial gravity, and closed its cutting heads to prevent lethal dust storms, and is managing its nuclear core to provide power and thrust while rejecting waste heat through massive radiators.
Takes a deep breath just thinking about it.
Right. Now we hit the true economic climax of the entire operation. The robot has a hopper full of crushed rock and metal. How do we actually separate the trillion-dollar platinum from the worthless dirt?
Ah, the refinery.
This brings us to the refinery. And just like everything else, microgravity completely breaks our terrestrial assumptions.
Yeah, the vast majority of terrestrial metallurgy and refining relies fundamentally on the constant pull of Earth's gravity. If you want to separate dense, valuable metals from later worthless rock on Earth, the simplest method is to melt the ore.
Because the heavy metal physically sinks to the bottom of the crucible, and the lighter silicate slag floats to the top where it can be skimmed off. Gravity does the sorting for you.
Exactly. But in the millage environment of a 100-meter asteroid, there is no down. Nothing sinks.
So if you melt it.
If you apply intense heat and melt an asteroid in microgravity, you do not get a neatly stratified pool of metal and slag. Surface tension becomes the dominant physical force.
Yeah.
You end up with a chaotic, bubbling, floating emulsion of molten rock, liquid metal droplets, and expanding gases trapped within the melt. It is an unmanageable, highly dangerous physical state.
Yet, almost every conceptual space mining proposal I've seen in popular media suggests using giant deployable space mirrors to focus sunlight and simply melt the entire asteroid into a glowing puddle.
Oh, I know, it's everywhere.
The architecture documents explicitly use this as a foil to demonstrate what not to do. If focusing the sun is so energetically easy, why is bulk melting catastrophic?
Well, it hits two insurmountable physical walls. The first is the sheer energy requirement. The heat of fusion required to melt solid silicate rock is roughly 1.4 megajoules per kilogram.
That's a lot.
Attempting to melt a million-ton body, or even large chunks of it, requires an astronomical influx of energy. A moving asteroid sweeping through a focal point of concentrated sunlight simply wouldn't dwell in the hot zone long enough to melt through.
But the second wall is the separation wall, which we just outlined. Even if you possess the energy to melt the bulk rock, you intentionally create the exact floating emulsion problem. Bulk melting takes a difficult separation task and transforms it into the hardest possible physical state to manage in a vacuum.
Which is why the entire paradigm of the refinery shifts. The golden rule of asteroidal refining is dry, contained, and gas phase. You absolutely never melt the bulk of the rock. The refining chain must be completely blind to the absence of gravity, executing the separation through magnetism and chemistry.
Okay, let's walk through that. The architecture breaks this down into a four-step sequence. Step one is dealing with the volatiles.
Right.
Before any aggressive grinding or processing begins, the raw feedstock is gently heated inside a sealed chamber using solar concentrators. The goal is not to melt the rock, but to drive off the volatile compounds, water, carbon dioxide, and complex organics, turning them into vapor that can be pumped away.
And if the robot is currently stationed on a carbonaceous C-type asteroid, this isn't just waste removal. This is actively harvesting the water for propellant.
Right.
And crucially, harvesting the carbon monoxide reagent that the refinery will desperately need in the final stages.
Wow, okay. So once the material is baked dry, step two is the cold grind. The dry, brittle residue is mechanically crushed inside a heavily sealed comminution drum. The goal is to grind the material down to a particle size where the metallic grains are physically liberated from the surrounding silicate matrix.
Which brings us to step 3, where we execute the primary metal cut, magnetic separation.
Because magnetic fields are entirely indifferent to gravity.
Exactly. The metallic fraction of asteroidal material is predominantly a native alloy of iron, nickel, and cobalt, all of which are highly ferromagnetic. By passing the crushed dry powder across a strong magnetic field gradient, the magnetic forces violently pull the iron alloy away.
Leaving the inert, non-magnetic silicate rock dust to continue down the line.
Yep. But the target of this entire trillion-dollar infrastructure is not iron. Iron is abundant and cheap on Earth. The economic drivers are the platinum group metals, or PGMs, platinum, iridium, osmium, palladium.
And these elements are not inherently ferromagnetic, so terrestrial logic would suggest they might be left behind in the silicate waste.
Right, but geochemistry provides a massive, highly fortuitous advantage here.
Yes, the PGMs in asteroidal material are classified as siderophile elements, which literally translates from Greek as iron-loving.
Such a great term.
It really is. During the formation of the solar system, these precious metals bonded intimately with the iron. So when the magnetic field grabs the iron particles and pulls them out of the crushed rock, the exceedingly valuable platinum group metals ride along trapped inside the iron matrix.
You execute a simple magnetic sweep, and you instantly achieve a highly concentrated PGM-bearing metal powder perfectly separated from the bulk rock.
It is an incredibly efficient first cut. Now, the architecture does specify a secondary sweep using electrostatic fields and eddy currents to catch any non-magnetic conductive metals that slip through.
Utilizing Lenz's law.
Right, where a changing magnetic field induces an electrical current within a conductor, which in turn creates an opposing magnetic field that physically pushes the conductive particle away. So you can sort the remaining valuable metals without relying on gravity or melting.
Okay, so we now hold a concentrated metallic powder. But we face a severe economic problem. This powder is roughly 99% iron and nickel, and perhaps 1% or less of the precious platinum group metals.
And we cannot afford the delta V to ship thousands of tons of structural iron back down Earth's gravity well. We only want the refined platinum.
Exactly. So how do we separate the trace platinum from the bulk iron and nickel without melting the entire mass?
This is where the architecture deploys step 4, which is just a masterpiece of historical industrial chemistry adapted for the vacuum of space. It utilizes the Mond process, also known as carbonyl refining.
Right. Discovered by Ludwig Mond in 1890 to refine terrestrial nickel. And it represents the ultimate gravity-blind separation technique because it operates entirely within the gas phase.
The chemistry here is fascinating. Let's walk through exactly how the Mond process attacks this powder.
So the concentrated iron nickel platinum powder is moved into a reaction vessel.
Ah.
Carbon monoxide gas is pumped into the chamber and passed over the metal at a very mild temperature, precisely controlled between 50 and 60 degrees Celsius.
Okay, pretty mild.
Very mild. Under these specific thermal and pressure conditions, the carbon monoxide molecules react chemically with the solid nickel atoms to form a highly volatile compound called nickel tetracarbonyl.
Wait, the solid metal literally reacts to become a gas at room temperature?
Exactly. The solid nickel simply evaporates into the gas stream.
That's incredible.
And if you slightly increase the temperature and pressure, the iron follows suit, reacting to form iron pentacarbonyl, which is also a gas. But crucially, the thermodynamic properties of the platinum group metals dictate that they do not form carbonyl gases under these mild conditions. They remain perfectly solid, inert dust.
It feels like absolute alchemy. You blow carbon monoxide gas over a pile of crushed metal. The iron and nickel physically vanish into the air, leaving behind a highly purified, ultra-concentrated pile of pure platinum dust.
It's beautiful, isn't it?
The separation is flawless, and gravity is entirely irrelevant. But what happens to the massive volume of iron and nickel gas that you just created?
The gas stream is piped away into a separate deposition chamber and heated to roughly 220 to 250 degrees Celsius. At that elevated temperature, the thermal energy breaks the molecular bonds of the carbonyl gas.
So the carbon monoxide releases its hold.
Yep, it reverts back to a free gas, which is immediately pumped back to the start of the loop to be reused. The pure iron and nickel drop out of the gas phase and deposit as solid metal.
The architecture notes, you can deposit this metal directly into molds, or utilize it as a feedstock for chemical vapor deposition.
Yeah.
Like literally 3D printing structural replacement parts for the robot in space using the extracted asteroid iron.
Yes.
And the absolute brilliance of this system is the source of the carbon monoxide. We didn't have to launch tanks of it from Earth. The fleet harvested the carbon and oxygen directly from the volatile C-type asteroids during Step 1.
The ecosystem literally feeds its own chemical processes.
It is an incredibly robust, closed-loop supply chain, and it adheres strictly to the final economic rule of the refinery. Tailings stay in space. Dropping millions of tons of processed silicate slag down through Earth's atmosphere is an ecological and economic disaster.
Right. In the architecture of the swarm, that waste rock is highly valuable inventory. It provides the thick radiation shielding for the robotic chassis, it provides the reaction mass for the thermal rockets, and it serves as raw construction material for future orbital infrastructure.
So the only material that ever makes the expensive, tightly controlled journey back down Earth's gravity well are the ultra-dense, ultra-valuable platinum group metals.
Exactly.
The chemistry is stunning, but reading through the technical specifications of the Mond process reveals a massive, screaming vulnerability. Nickel tetracarbonyl glass is profoundly toxic, and the operating environment is highly corrosive. You are running delicate pressure vessels, high-speed gas recycle loops, thermal sensors, and heating elements, all bathed in corrosive gases and surrounded by highly abrasive, statically charged asteroid dust.
Oh, yeah. Mechanical failure is an absolute certainty. Parts will fracture, pipes will corrode, actuators will jam with silicate dust.
Which introduces the ultimate operational hurdle.
Mm-hmm.
These robots are operating millions of miles away in the asteroid belt. The speed of light imposes a communication lag that can be anywhere from 10 to 40 minutes round trip. If you are a human operator sitting at a console on Earth and a pressure valve in the carbonyl refinery jams, you are watching a catastrophic failure that actually happened 20 minutes ago. Teleoperating delicate repairs with a joystick over a 40-minute delay is physically impossible. When this machine breaks, who fixes it?
This is where the architecture fully integrates the foundational white paper on self-repairing legged robots. To survive the light lag and the corrosive environment, the machines must possess a localized autonomous fault recovery system.
They must be capable of diagnosing and repairing themselves in real time.
Yes, and the core of this capability relies on a concept called an internal self model.
The self model is essentially a highly detailed digital twin of the robot running continuously within its own computer brain. It possesses a full kinematic and physics simulation of its own body.
Correct.
So if a fault occurs, say a micrometeorite strikes a leg and seizes a joint, or the abrasive dust strips the gears in a cutter head, The robot's internal sensors detected discrepancy. The physical leg did not move to the angle the software commanded.
Right. And upon detecting that discrepancy, the robot isolates the error and injects that specific physical damage into its internal avatar.
It's like if you or I break an ankle, we don't just mindlessly stumble around repeatedly putting full weight on the shattered bone until we accidentally figure out how to walk.
Hopefully not.
You pause. We consciously simulate different ways to limp within our own minds. We imagine shifting our weight to the heel or swinging the leg wide, visualizing the pain and the physics before we ever move a muscle. We run simulations until we find a limp that seems viable, and then we physically try it.
The robot is utilizing its self-model to do exactly that.
That's so cool.
To discover that new compensatory way of moving, the architecture utilizes a specific evolutionary AI algorithm known as neat neuroevolution of augmenting topologies. NEAT does not operate in the physical world, it operates entirely inside the damaged simulation. When the robot is injured, NEAT begins breeding thousands of candidate neural control networks.
And it isn't just tweaking the mathematical weights of an existing network, right? The augmenting topologies part means it is literally evolving the architecture of the brain. It adds new simulated neurons and new synaptic connections, testing each mutated brain against the physics of the simulated asteroid environment to see if it can restore forward locomotion despite the frozen joint.
Yes. It creates a massive evolutionary pressure cooker within the span of a few minutes, evaluating thousands of generations of controllers until it discovers a network that successfully routes around the physical damage.
Wow.
But the paper outlines a critical optimization strategy to prevent the AI from wasting time. It uses deconstruction-biased repair.
Let me guess. If a complex multi-legged walking gait fails, the AI doesn't simply throw away the entire brain and start evolving from absolute zero.
Nope.
It takes a known, previously working motion, perhaps the gait from the uninjured opposite leg, and slowly prunes it down. It simplifies the network, removing nodes to find the absolute smallest possible edit required to fix the immediate problem.
Exactly. It also bounds the search space hierarchically. It does not attempt to rewrite the entire vehicle's locomotion software immediately. It attempts to evolve a localized fix for just the single broken joint.
And if that fails?
If that fails, it expands the scope to rewrite the control software for that entire leg. Only if that fails does it attempt to evolve an entirely new asymmetric limp for the whole machine.
It is a brilliantly efficient triage system. But a software simulation running in a pristine computer memory is never a perfect representation of reality. There's always a reality gap between the physics avatar and the messy, chaotic environment of a rubble pile asteroid.
Right. So once NEAT evolves a theoretical solution, the robot must physically test it before committing to the new brain. The researchers term this the physical verification step. We can call it the ant dance.
The ant dance. The robot uploads the newly evolved controller to the damaged limb and executes a series of highly constrained, probing physical movements. A slight shift of its mass, a tiny extension of an actuator, feeling the physical resistance.
Yes. It is actively testing the simulated repair against the real-world friction of the rock, the milligravity, and the tension of its anchor cables.
If the physical dance validates the simulation, the repair is committed to memory. If the physical test fails, if the leg slips or the torque limits are exceeded, the robot uses that failure data to update and correct the physics of its internal avatar, and NEAT begins a new cycle of evolution.
It is a profound level of physical self-awareness. But Section 7.1 of the white paper flags a massive diagnostic trap within this loop. How does the robot functionally distinguish between internal physical damage and a hostile external environment?
Oh, right. Because if the mechanical anchor drilled into the asteroid slips through crumbled rock, the leg will drop unexpectedly. The internal sensors will immediately report a catastrophic deviation from the expected angle.
And if the robot naively trusts that sensor data, it will inject a broken leg into its avatar and permanently mutate its brain to fix a perfectly healthy limb.
Effectively crippling itself to compensate for shifting sand.
Exactly. This requires the diagnostic system to move beyond simple sensor readings and engage in logical inference. The discriminator between self-damage and environmental disturbance is persistence and correlation.
If a fault is truly internal, a stripped gear, or a severed cable, that mechanical error will persist and travel with the robot. It will manifest regardless of what orientation the robot is in or whether it is anchored or floating.
Right. However, if the error correlates heavily with the external environment, for example, the leg only slips when the anchor winch tension peaks, or the sensor noise pulses rhythmically in exact time with the rotation of the asteroid, the robot's diagnostic inference engine must deduce that the environment is causing the disturbance, not its own chassis.
It has to logically realize it is standing on a crumbling, spinning rock rather than concluding it has a broken knee. And this leads to what the text describes as the absolute hardest engineering problem in autonomous robotics: intermittent faults. What happens when a component isn't permanently broken but only fails occasionally?
Yeah, that's the nightmare scenario. The paper provides the example of a magnetic tracker that functions perfectly at room temperature but fails completely when it gets hot. The robot detects the failure, pauses, utilizes NEAT to evolve a software workaround, and performs the physical ant dance.
But during the time it took to evolve the fix, the component cooled down and began functioning again.
Yep. The physical ant dance succeeds. The robot assumes the fault is cleared, and it resumed operation. 10 minutes later, the component heats up and fails again. In traditional engineering, a no-fault found diagnostic simply means that the fault is not present here and not present now.
But in the context of a mining robot operating adjacent to a thermally cycling nuclear reactor, a component that unpredictably phases in and out of functionality is a lethal hazard. The robot's solution to an intermittent fault is to develop machine suspicion. A single successful ant dance does not absolve the failing part. The suspected component is placed on a persistent internal watch list.
If the part fails again under load, the diagnostic system essentially learns to hold a grudge. It realizes it cannot predict the failure state and therefore decides to permanently route around the component.
It artificially reclassifies the intermittent part as permanently dead, because a predictably dead leg that you can evolve a reliable link for is infinitely safer than an intermittent leg that betrays your balance during a critical nuclear burn.
We are firmly in the realm of machine psychology at this point. The robot is learning to distrust its own untrustworthy servos. But the architecture reveals one final masterstroke layer of resilience. The mother miner, the massive reactor-bearing robot executing these thermal burns, is not facing these challenges alone.
Right. We mentioned earlier that the mother deploys a swarm of child robots. These children aren't just redundant cameras or mapping drones. They are absolute structural necessities for the mission to close economically and physically.
The swarm topology is the answer to almost every insurmountable bottleneck we have discussed today. Recall the throughput wall in Section 1. A single mother machine cannot physically grind rock fast enough to despin the asteroid before its operating life expires.
And the child robots solve this. Dozens of small, highly specialized children are deployed around the asteroid's equator, acting as a distributed swarm of tiny mass slingers. They multiply the throughput in parallel, completing the D-spin operation in days rather than years.
Exactly. They also provide the shared external sensing layer. The mother robot utilizes internal proprioception. She can only feel her own joints from the inside.
So if her central chassis becomes physically warped by the immense thrust of the nuclear engine, her internal angle sensors might not register the deformation.
Right. The child robots station themselves a few meters away and optically observe the mother. They act as an external truth matrix, transmitting data that tells the mother, your internal simulation is incorrect. Your spine is visibly bent 3 degrees to the port side.
Furthermore, they act as the shepherds we discussed earlier, remaining on the redirected asteroid to provide the vital, years-long trajectory corrections back to Earth. But their most fascinating role is acting as a distributed Beowulf cluster of external compute power.
Oh, I love this part.
A Beowulf cluster is an architecture developed in the 1990s where you network a swarm of ordinary off-the-shelf computers together to act as a unified supercomputer. When the mother robot is heavily damaged, she is likely engaged in a high-stress operation. The asteroid is spinning, the nuclear reactor is running hot, she is actively managing thermal loads.
Right, she does not have the spare processor cycles or the electrical power to run tens of thousands of neat evolutionary simulations internally.
So she offloads the cognitive burden. She broadcasts her telemetry and her physical constraints via laser or radio link to the surrounding swarm of children. I am crippled, here is my sensor data, here are my current thermal limits. The child robots pool their parallel processing power, run the evolutionary simulations for her, and simply beam the compiled, optimized solution back to the mother's control matrix.
It is a stunning display of distributed survival. And finally, the children provide the one capability that a software self-model absolutely cannot: A simulated avatar can figure out how to limp on a broken leg, but software cannot reseat a corroded chemical connector in the carbonyl refinery. Software cannot replace a shattered drill bit.
A specialized child robot, equipped with delicate manipulator arms, can navigate the standardized docking hardpoints on the exterior of the mothership. It can physically cut away the damaged pipe and weld a 3D printed replacement into the refinery loop.
Yep. The child robots convert the mother strategy from simply adapting around the broken part into physically replacing the broken part. The swarm functions as the autonomous immune system for the entire architecture.
It is a holistic, incredibly hostile ecosystem. We have covered a massive amount of physical and chemical territory today. Let's pull back and synthesize what this architecture truly represents. What we've examined is a complete masterclass in inverting human engineering intuition. Almost every instinct we brought from terrestrial mining and rocketry proved to be a fatal liability in deep space.
Absolutely. We instinctively believed that high-efficiency imported hydrogen fuel was the only viable path for deep space propulsion. The architecture demonstrated that running a nuclear engine on free, local, low-efficiency vaporized rock and water is vastly economically superior.
We believed we needed massive, heavy machines to anchor a drill into solid rock. The architecture proved that in microgravity, you must abandon mass entirely and manufacture your own gravity using mechanical tension or continuous engine thrust.
We believed that the simplest way to refine metal was to apply massive solar heat and melt the asteroid. The architecture proved that melting creates an uncontrollable emulsion, and that you must meticulously contain everything, keep it completely dry, and utilize gravity-blind gas phase chemistry like the MON to process.
We believed that a trillion-dollar mission required perfect, centralized control from human operators on Earth. The architecture proved that due to light lag, survival and resilience must be localized, living entirely within the physical body of the robot and the distributed minds of the local swarm.
And fundamentally, we believed that the task required one massive, heroic, sci-fi megaship. The brutal math of the throughput wall proved that a swarm of small, disposable, island-hopping machines is the only mathematical way to execute the mission before the hardware degrades.
The sheer interlocked scale of this vision is breathtaking. It is not merely a mining blueprint.
No, it's much more than that.
And that leads perfectly into the final, slightly chilling thought I want to leave you with today. It's an extrapolation the expert and I were discussing before we started recording. When you step back and look at the integration of all these subsystems working in tandem, think deeply about what this architecture actually describes.
Yeah, we are talking about deploying a massive distributed swarm of highly autonomous machines. They are equipped with evolutionary AI that constantly mutates its own neural pathways to survive physical damage.
They possess megawatt-class nuclear reactors, providing immense, decades-long power.
They actively hunt and harvest water and carbon across the solar system to fuel themselves.
And they possess an onboard chemical refinery capable of extracting pure metals and 3D printing their own structural replacement parts.
So if we launch this fleet and we program them with the fundamental hard-coded mandate to adapt, survive, and relentlessly optimize their harvesting out there in the deep, unmonitored dark of the asteroid belt.
At what point does this operation stop being a human mining supply chain? At what point does this become an artificial silicon and steel ecosystem with its own evolutionary trajectory?
Right. If they can mutate their minds, harvest their own energy, and print their own bodies, they possess all the prerequisites for life.
If they mutate beyond our original parameters, they can begin reproducing and optimizing completely beyond our ability to recall or control them.
It is a technological architecture explicitly designed to survive and function entirely without us. The ultimate question is not whether it will work, but what it will choose to become once it realizes it no longer needs us at all.
It is a terrifying and brilliant paradigm to mull over the next time you look up at the night sky and wonder what is waiting for us in the dark. We'll leave you with that. Until next time, keep diving deep.